Hello everyone, and welcome to another MCAT ACE lecture. In today's lecture we will be covering acid and base chemistry, and this is part 2 of this series. So if you missed part 1, please go back and watch the acid and base chemistry part 1 video, because this is going to build on the concepts in that video. So a general overview of what we'll be covering here. We have pKa and Ka review. We discussed this in much more detail in part 1, so we'll just be doing a brief review of that at first because it's going to be important for some of the equations and titrations we look at in this upcoming part. We'll take a look at buffer solutions and conditions, briefly mentioning what a buffer is and why it's important to maintain high levels of acid and its conjugate. We will then take a detailed look at the Henderson-Hasselbalch equation. And especially we want to take a look at when the pH is equal to the pKa in that scenario, which leads into titrations. So for titrations, when we get ready to mix acid and base together, we're going to take a look at 3 very important examples, which is a strong acid with a strong base, so maybe something like HCl and NaOH, a strong acid and a weak base, so that could be something like HCl and ammonia. And then we would also look at a weak acid and a strong base, such as acetic acid and sodium hydroxide. All right, and then we will briefly cover indicators. There will be a chart that I can bring up just to take a look at the different indicators, because you want to pick your indicator based on the various pH ranges that you're looking to titrate at, and that can depend on the strength of your acid or base involved. And then, as usual, we will wrap up with a practice session, especially since we already had part 1, we need to practice some questions regarding acid-base chemistry. So let's go ahead and get started with the general but brief review of pKa and Ka. So just a brief recap here. When we deal with Ka, we're talking about the acid equilibrium constant, and for equilibrium, we're talking about weak acids, not ones that would dissociate completely. So with a weak acid, you'll also have a weak, or you could be a strong, but a conjugate base. Okay, and you'll also have your H+, or if it's aqueous, that might be H3O+. And then you will also have, on the bottom, your HA. Okay, so Ka, the larger Ka is, the stronger the acid. Now we can also get pKa, and as we stated in the first lesson, pKa, similar to pH, is a very handy and common way to refer to the strengths of acid on a numerical scale that doesn't have quite as many exponents. So when we get ready to do pKa, all you have to do is the negative logarithmic transformation of Ka, and that'll give you pKa. Now, pKa, because it's a negative logarithmic transformation, is going to have the opposite effect in the fact that as you get lower in pKa, the acid is going to be stronger. Now keep in mind, the same thing is true of pH, which takes the H+ concentration and it does the negative logarithmic transformation of that. And when we get pH, the lower the pH, the stronger the acid. So when you get into these P scales, you're flipping the tables in terms of having lower values making for stronger acids. Okay, so that's a general recap of Ka and pKa. Now, in terms of buffers, buffers are very, very common, and we talk about them all the time in relation to biochemistry, physiology. The human body has to deal with a lot of buffering for blood. And so buffers are a very important concept. And when you have a buffer, you will need 2 things. Number 1, you will need a weak acid or base. Usually it's a weak acid that's picked out, but you can have a weak base. And then the second thing that you will need is going to be the salt conjugate. Okay, so in other words, you need the conjugate base or acid respectively when you get ready to make this up. So a common example would be the acetate buffer. So when you have acetate, it's referring to the acetic acid, which is a weak organic acid. It's a carboxylic acid. Okay, plus if you want to make it an acetate buffer, you're going to need to add a salt version of the conjugate base. So something like sodium acetate. Okay, and when you have these two, this is important because this is an acid and base, and if you're going to pick out an acid and a base for a buffer system, you have to make sure that the two will not neutralize one another in a reaction. So picking out something like HCl and NaOH would not be appropriate because HCl would give off H+, and then NaOH would give off OH-, okay? And the two of these are going to make water a neutral compound. That's not going to work because they will react with one another. This is why you need a weak acid or base and its conjugate. So when we look at something like this, if the acetic acid were to give up this mildly acidic proton into solution, this conjugate base, the salt, could pick it up and it would create acetic acid. So you're basically in equilibrium. You're just batting the hydrogens back and forth and keeping the concentrations fairly consistent. And this is very important in terms of a concept for a buffer system. Now, when you have a buffer of interest, you want to make sure that you're picking out an acid that's going to have a pH in the range that you would like to buffer at, okay? So if you want to buffer in a region of, let's say, 3.5, then it's important that the acid you pick out has an approximate pH of 3.5 when you're looking at that buffering region. And it's also key that you want to make sure you use much acid, okay, and approximately an equal amount of base. Now, the reason that you want to use a lot of acid is because if you're trying to buffer, let's say that you've got this system over here and then some hydroxide is dropped into this system. When the hydroxide hits this system, it is going to deprotonate, okay, the acidic hydrogen that is found here. And in a case like that, you need to make sure that you have an ample amount to stay in this pH range, okay, that the hydroxide is not going to just come in and basically obliterate a very small amount of acetic acid that's present there. So you need to keep your concentrations relatively high, but the concentrations of acid to conjugate base, or vice versa, base to conjugate acid, need to be approximately similar in order to create an effective buffer system, right? And when we look at titration curves, we will see what's called buffer regions as we're starting to titrate with the weak versions. The strong acid, strong base, you're not going to see that. And again, that's because it requires a weak one. Otherwise, you'll have a reaction like that, where we showed hydroxide going to water. Okay, now let's discuss the Henderson-Hasselbalch equation. So the equation itself connects pH to pKa, and it says that pH is going to be equal to pKa plus, and you're going to take the log of the conjugate base over the acid concentration. Okay, so this whole thing, you're going to take the log of this, and this equation is going to allow you to solve for pH, pKa, or the concentration of acid or conjugate base if you have those other pieces there. Now, this is a very, very important equation, particularly when you get ready to start looking at titrations and weak systems with buffering, because there's something that is very important here. There is a point in this system, or this equation, where the pH is going to equal exactly the pKa. And that is when the log of this ratio is equal to 0. Because if pKa plus 0 is equal to pKa, then the pKa will be equal to the pH. So in a situation like that, how would we get log of this proportion here to equal 0? Well, what we would need to do is we would need it to be log of 1, because the log of 1 is going to be 0. And in order for it to be the log of 1, we have to have A minus and HA at the same value. So when your conjugate base is equal to the concentration of your acid, your weak acid, At that point, you get a log of 1, and when you have a log of 1, that equals 0, and when you have 0, the pH is equal to the pKa. So, the pH is equal to pKa when you have equal concentrations of a weak acid and its conjugate in solution. Okay, and again, when we get ready to start looking at titrations here, we will see how this plays out on titration curves, because you have what's called the equivalence point, which is when you have an equal amount of the base and the acid, but then when the weak acid has its conjugate, we're going to find that about halfway to that equivalence point is where we will strike this balance, and we'll find the pH is equal to the pKa. So, since we keep talking about titrations, let's go ahead and take a look at a titration for a strong acid with a strong base. So when we take a look at a strong acid, strong base titration, or any titration for that matter, you will have the volume of either your acid or base along the x-axis, and then your pH along the y-axis. So in this case, we're going to talk about adding the NaOH as the titrant. So we start off with some solution of acid. Now, if it's a strong acid, we're going to expect that the pH would start off low. So when we get ready to start off, it's probably going to be somewhere down around here, okay? Assuming that this is, let's just say, a pH of 1, all right? And then what you'll see for a strong acid, strong base is that this is going to stay consistent for a pretty long time with a very ever so slight rise. And then suddenly, at some point, it's going to jet off really, really high. And then you'll start leveling, and this leveling will climb up a little bit, but it's pretty much going to level off like this. And this would be a strong acid, strong base situation. Now, when you get to the equivalence point, which is also known as the inflection point, is going to be right in the middle of this jump here. And if you go over and you look on your pH scale, if you were to actually do this in an experiment and graph it, you would see that the pH is going to be right around 7. And that would make sense when we have a strong acid and strong base. So again, the example where we have HCl and NaOH, right? What we're going to produce is water, and water is neutral. It has a pH of 7. So this is exactly what we would expect in a situation like this, okay? Now, the leveling here is because these are both strong acid and strong base. So we don't see a gradual climb like so, and then suddenly a jump up and then another gradual climb, okay? That would be something more along the lines of a weak acid or base that you could potentially see something like that. When it's strong, a strong acid is going to keep a very, very low pH until all of a sudden the OH matches the H+. And at that point, we have a very sharp jump because we pass through a neutral point where all of the acid has run out and all of the base has reacted with it to give water. So we essentially just have water in solution. And then all of a sudden I add 1 or 2 drops of base past that neutral water solution, and now the solution has an excess of OH minus, hydroxide. And OH minus is very basic. It's a strong base. So then all of a sudden we see another leveling where the level is going to be very high, and we would expect maybe this is around, somewhere between 12 to 14, 14 being the strongest. Let's just say 13 in the middle for this. And you see these extremes when you do strong acid, strong base titrations. We do not have a buffer region because when we talked about buffers and Henderson-Hasselbalch, we said we needed a weak acid or base. And when we're talking about that, you can see a weak acid and its conjugate appearing here in this system. HCl and NaOH are both strong, so we cannot apply the pH-pKa system or any type of buffering in a reaction like this because it's exactly that. It's a forward-moving reaction. There is no equilibrium associated with this. So that's strong acid and strong base titrations. The next one we want to look at is a weak system. And so on that case, we will take a look at a strong acid and a weak base. Okay, so in this next example, we're going to take a look at the strong acid and weak base. And if you see down here, I have the volume of the strong acid as the titrant this time. So that means the base is what we're going to be starting with. Now, if we start with a base, particularly a weak base, so we can just pick out something, let's say ammonia, because we've been going through that example. Keep in mind that the conjugate, or the A minus conjugate base for ammonia is going to be, I should say conjugate acid, NH4+. Okay, and NH3 would be the conjugate base of the ammonium ion there. So what you'll start with is, certainly you'd be up in the more basic region. However, when you start here, you're probably going to be starting somewhere around 10 to 11 on a pH scale. It could be slightly lower depending on the base. But when you're dealing with a weak base, you shouldn't be having pH values of 13 or 14. That would primarily be reserved for a strong base. So when you do this, you're going to see a gradual decreasing, and then suddenly it's going to tail off into a slope, and that's when we hit our equivalence point. And it's going to go pretty far down before it levels off here. And again, when it levels off, the pH here is probably going to be around 1 to 2. All right, now the reason for that is we're dealing with a strong acid. So what happens is the strong acid will rapidly give off its protons, and the base will pick it up, which is going to decrease the amount of pH in solution. And then as that's going along and more H+ is being liberated into the ammonium ion, at a certain point you're going to saturate all of the ammonia into ammonium using the H+. And at that point we again would hit our equivalence point, right? Now, because we're dealing with a weak system here, you can trace down and say at a given volume, and we'll call that volume X, X is going to be the volume at which the equivalence occurs. And for an equivalence point, you have to have equal moles of acid to base. So moles of acid is going to equal the moles of base, and that would be at X volume. Now, what we can do with the Henderson-Hasselbalch equation as we look at this sort of stuff is we can say, what is the pKa of the ammonium ion? And the pKa for ammonium, it turns out, is around 9.25. So if we were to come up here, and this is an approximation, but if we found the volume that was half of the equivalence volume. So this volume right here is going to be 1/2 X volume. This point, in terms of its pH right here, would be a pH equal to 9.25. And that's the pKa of the ammonium. So if you go back and you look at the Henderson-Hasselbalch equation, remember we said when these values equal one another, okay? So this does not have to do with the HCl that's present. We're looking only at the NH3 and the NH4+ that are in comparison with one another. And so the equivalence point is when all of that NH3 has been used up by the strong acid. So halfway there means that you've lost half of your NH3. So half of your NH3 remains. And the other half of it would be in the form of the ammonium ion at this point. And if you have equal concentrations of your acid and conjugate base, or base and conjugate acid, either way you want to look at it, you will have that 1-to-1 ratio. And the 1, when you take the logarithm, will go to 0, and that drops out where the pH will equal the pKa. So that is an example using a strong acid and a weak base where we can do some prediction of that sort of behavior. Now, one other important point here. The equivalence point, okay, if you were to look at the pH here for this equivalence point, the pH would be lower than 7. Okay? So it would be below 7. Maybe it would be somewhere around 6 or 5.5. Again, these are just rough estimates. However, when you get ready to look at using a strong acid and a weak base, you're going to have a equivalence point that is lower on the pH scale than 7. So remember, in the example with the strong, water was what we were producing. Water is neutral. It has a pH of 7, and so that's exactly where we expect the equivalence point to be. So maybe here the 7 mark is right here, and we're coming in underneath of that. Okay, and the main reason for that is, yes, we are using a strong acid, but as we add the strong acid to the base, we do not create a neutral compound. We create NH4+, and NH4+ is a conjugate acid. So this compound that's resulting here is acidic. Now, it's not as acidic as HCl, so we wouldn't expect the equivalence point to be 1 or 2 in pH. However, we do expect it below 7 because NH4+ is more acidic than H2O is. And so at that point, when you get to the equivalence point, you expect the pH to be lower than 7 there. So let's take a look at one more titration. We're now going to look at the weak acid and the strong base, and we'll start back off in the acidic region in this one and work our way up. Alright, so for this final example, we're going to take a look at a weak acid and a strong base titration. So I've changed this down on the x-axis again to volume of sodium hydroxide as our strong base. And what we can go ahead and do is start off at a pH, and the pH is going to probably be, if it's a weak acid, somewhere more in the realm of 3 to 4. All right, so you're not going to be starting as low this time, and you will have a gentle ramp up as you continue to climb, and then suddenly you'll hit a point where you go up, and then you will level off high. Okay, that's a little too high there, just because we were going past the axis there. Okay. So, as you move towards your equivalence point, a couple of things to note here. The equivalence point right here, okay, this time, if I come over, I expect this to be at a pH above 7. This is because we're using a weak acid and a strong base. All right, now, from that equivalence point, if I take that volume and I cut the volume in half, I would expect to find the spot where the pKa is going to match the pH. So let's do the other weak acid we were talking about, which was acetic acid. Acetic acid has a pKa of 4.76, so the pH here would be 4.76, which is equal to the pKa of the acetic acid. Okay? Now, as the NaOH would be added, you would create the acetate ion by removing the acidic hydrogen on acetic acid, and you would create sodium acetate. Now, this is a conjugate base that's being formed. And because we're not forming water, the same premise is going to apply. I'm forming a base in solution, and if I form a base in solution after I add the sodium hydroxide, then at the equivalence point where there's an equal amount of the acetic acid to NaOH in terms of volume, or in terms of moles, excuse me, at that point your conjugate base is going to be building up, and so the point would be at a pH above 7 because you have a basic product that's coming out of that, not an acidic one or a neutral one. And then you would climb off, and again up here, because this is strong, we would be talking about something probably in the realm of like 12 to 14 because of the sodium hydroxide. Now, one other thing I wanted to mention, when you get into this region that contains the half volume of the pKa for the pH with the Henderson-Hasselbalch equation, this is known as the buffering region. Okay, so you can see While there is climb, it stays somewhat steady despite the fact that we are dropping sodium hydroxide into it. But at a certain point, you will override the buffering capacity as you continue to add strong base and pile it on, and at that point you start to shoot up quickly, you hit an equivalence point, and then the solution obviously becomes very basic afterwards when you have hydroxide that is sitting around free in solution after the titration is over. So those are the three major types of titrations. You can have a weak acid and a weak base. Those can be very unique. They also tend to not have very distinct equivalence points or very distinct lines or drop-offs anywhere because you're dealing with a weak and a weak. So it's all just a very gradual snaking type of figure that you get when you have an example like that. These are by far the three most common that you would come across. So now that we have discussed that, if we go back up and we look at our checklist, we've covered all the different types of titrations and we have an understanding of when the pH is equal to the pKa. We're going to take a brief look at indicators. I'll bring up the indicator table that I have, and then we will move on to the practice questions for the final part of this lesson. So let's go ahead and take a look at indicators next. Okay, so what I have brought up here is an indicator table, and this table shows the various colored indicators that can be used during titrations. So having an indicator is very important when you're getting ready to do titrations, particularly if you want to see or attempt to see right after the equivalence point has been reached. And when you do that, you can do it using a color change. So some of these are more common than others, but they are all various options that give us a span of pH range where we can use them. Now you can also go ahead and you can do a titration with a pH meter and just monitor the pH as you go along. However, when you do your indicator, it really gives you a clear distinction in terms of when the equivalence point has been reached. So a couple of options here. You have thymol blue. Notice that you have acid and base and they have different colors. So the whole premise behind this is once you go from what's considered the acidic solution into a base solution, you are going to end up with a different color change. Now these are relative terms. So when we look at pH, we consider base to be 7 and above, where 7 is neutral, but anything above that is considered base, and acid is anything below 7. However, when you see acid and base, acid is simply referring to the region which you would have up through the equivalence point, and then the base is going to be the point right after that where you would end up having the color change. All right, so the various pH ranges can be found to the right. You have for thymol blue, red and yellow with 1.2 to 2.8, and bromophenol blue with yellow to purplish, bluish purple, at 3.0 to 4.6. Methyl orange and methyl red are both common indicators. They obviously, respectively, are orange or red in acid, and they both go to yellow. Their ranges are a little bit higher. They go from about 3 all the way up to 6 if you're using the methyl red. Then you have some of the blues, which are chlorophenol blue and bromothymol blue, cresol red, and then finally probably one of the best known is the phenolphthalein indicator. This one's popular because it is colorless, and then it will turn into a pinkish purple color. And the reason that phenolphthalein tends to be pretty popular is that you can start catching things that are further up in the basic region with that color change. So it's one of the indicators that can get above a 7, and really when you're doing strong acids, strong bases, 7 is the equivalence point, and then you start going above that. So all of those other indicators would be a little difficult, if not impossible, to be using when you've got a situation like that. So if you were to come across examples, this is not the type of thing you would be asked to memorize or know, all of these ranges and colors and things of that nature. But what you do need to be able to understand is, based on the type of titration that you may be doing, strong, weak, or strong, strong, etc., the optimal indicator to pick out, and that's going to be based on the pH range. The colors really don't have anything to do with it. That's, it starts at one color, changes at another, but the range at which you get the color change and where that's optimal is going to be very important, because that is the target that you want to be kind of in that range when you are attempting to do some sort of a titration where the equivalence point will fall in that range. So remember, not everything's going to be at 7. We had some where we had bases that were going to be above that and some that were below it when we had acid. So you need to pick out your indicator accordingly depending on the pH region that you are looking at. So that really covers the indicator portion. What I am going to do now is go ahead and bring up the questions for the pH and acid-base chemistry lecture. We will go through those as usual, and then we will wrap up this portion of our course. All right, everyone. So I have brought up the questions for the acid-base chemistry lecture here. We're going to go through them as usual, and I will scroll through the answers slowly, so pause it if you need to copy anything down or go through the question again, and then pause after we've done all of the questions and attempt to solve them yourself before unpausing it and going through the walkthrough. So, number 1, which one of the acid-base titration procedures shown below is most likely to correspond to the titration profile shown below? So you can take a look here at the titration curve that we have. Right? They note the equivalence point, and you can see the volume added on the x-axis and the pH on the y-axis. So this is similar to the examples that we just saw in the second lecture here. All right, now the options are A, acetic acid solution is added to aqueous ammonia. B, aqueous ammonia is added to acetic acid. C, aqueous sodium hydroxide is added to acetic acid solution. Or D, hydrochloric acid solution is added to aqueous ammonia. So you've got 4 different combinations of acid-base reactions, and you have to pick the best one that is represented by this titration curve right up here. All right, so pay attention to the wording and the order in which the words appear in these answers. All right, number 2, solutions of which of the following compounds in water are expected to display a pH of less than 7. So keep in mind pH of less than 7 and what that would mean in terms of acidity or basicity. And then you can look at your options here. We have potassium nitrate, potassium sulfate, cesium acetate, rubidium chloride, ammonium nitrate, potassium sulfite, sodium bisulfate, and sodium cyanide. So most of these are going to be salts when you look at them. In fact, all of them are salts of some sort. So the question is, of these grouped salts here, which ones, when they dissolve in water, would create a solution that has a pH less than 7? All right, and you can see the options here, 1, 2, and 5 only. And then you have 3, 4, and 7 only, 3, 6, and 8 only, and then 5 and 7 only. So those are the options for that. All right, and then number 3, this one's going to involve a little bit of math. When asked to titrate 30 milliliters of 0.1 molarity nitric acid with 0.1 molarity sodium hydroxide, a student chose thymol blue as the acid-base titration indicator. The indicator changed color from yellow to red when 20 milliliters of the sodium hydroxide solution had been added. What was the pH of the solution at the titration endpoint? All right. Now, I will let you know, you do not need to know the range for the indicator that is mentioned here, even though we had that up in a table a few minutes ago. Okay, now, if you have a question where you do need the ranges, they would be provided. Okay, this is not something you have to memorize. However, in this question, you should not need it, but we will discuss it as we go through the answer. So you can take a look here. We're looking for what the pH of the solution is at that titration endpoint. 1.35, 1.70, 2.50, or 7.00. Those are the options. So again, I'm going to slowly scroll through. For anybody that needs to pause, copy something down, take a screenshot, you can do that. And go ahead and work through these by yourself, get as far as you can, and then when you are confident or you get really stuck and you need to proceed forward, you can go ahead and unpause the video, and at that point we will go ahead and go through the walkthrough together. So go ahead and pause your video now and attempt to answer these questions. Okay, so hopefully everybody has had a chance to put in some effort onto these questions. Let's go ahead and work through them now. So number one, which one of the acid-base titration procedures shown below is most likely to correspond to the titration profile shown below? So what I want to do first, and what you should do when you analyze something like this, is just look at the titration curve and gather what information you can before you get into too much depth with your choices here, because we could easily do some process of elimination if we make some notes. So first thing, let's take a look at where this is starting. We're starting off near a pH of 12. So if we're starting off near a pH of 12, that means that we must be starting off with some sort of a base. All right? So anything that is suggesting we start with acid and add base to it would be the reverse. We'd be starting down low and working our way high. All right, so that's one thing. And then the second thing we want to look at is the general shape of the curve so we can try to classify it. Well, if you remember, when we were looking at curves for anything involving strong acids or strong bases, there was always a sharp drop at the equivalence point and then a leveling off. Now for the strong, there was a leveling on both edges, whereas when it was weak-strong, there was sort of a gradual decline, and then a strong drop, and then a strong leveling, right? So what we can see here is this is almost just a weak leveling off the entire time. There is no very evident equivalence point as far as an inflection right where the graph takes a quick drop like that. So what we can assume then is that we're dealing with a weak type of titration. Now this is not one that we went over specifically. We looked at the weak-strong examples, but you can have a weak, and these weak acid, weak base titrations have the most variability out of all of them in terms of the shape and where the pHs are going to start and end, where the equivalence points may be. All right. So strong acids and strong bases are more predictable in terms of their behavior, whereas weak acids and weak bases can have a lot more variability in terms of the starting and the ending points. So let's use this knowledge to do a little process of elimination. So first of all, the fact that we know we have weak means sodium hydroxide, that's strong. C must be out. Hydrochloric acid is strong. That also has to be out. So we're already down to a 50-50 shot. Now pay attention to the order in which the words are placed. For A, it says acetic acid solution is added to aqueous ammonia. That's plausible because ammonia would be a base. So we're starting off basic, and then we're going to add the acetic acid, which would allow it to decline slowly. These are both weak. And then we have for B, aqueous ammonia is added to acetic acid. This would be incorrect because if it starts with acetic acid, we would expect a low pH to gradually rise as the ammonia is added. And that's not what's happening here. We're starting at a basic pH, that was 0.1 that we came up with, and we're slowly declining. So just through process of elimination, we can see that A is the best selection. Acetic acid is being added to aqueous ammonia in a weak acid, weak base titration. All right, number 2, solutions of which of the following compounds in water are expected to display a pH less than 7? So the first thing you want to realize is that a pH less than 7 is talking about something that is in an acidic environment, not a basic environment. So 7 would be neutral, and then after that, you're talking about a base, all right? So if you look at a lot of these, you will end up with some sort of a base or conjugate base, because we have these anions here, right? So acetate, right? The acetate anion would be something that looks like this. Now, it's acetic acid when there's a hydrogen added to this carboxylic acid. However, if you have just a salt, right, at that point, you are no longer talking about it being acidic. So you have to be very careful to look at whether there is the presence of any type of hydrogen that is available, because we have to have hydrogen in order to make this acidic, at least from a Bronsted-Lowry perspective. We're not really talking about Lewis acid, Lewis base right now. So when we get ready to look at these, there are two good options here. You would have to draw all these out, okay? So you have potassium nitrate, that would be KNO3, again, no hydrogens. You want to do this for all of these. Potassium sulfate would be K2SO4, again, no hydrogen. So as you go through and you're looking at these, there are two that have hydrogens. Ammonium nitrate, the ammonium is NH4+, and nitrate is NO3-. Now what we know from our lectures and examples is that ammonium is a weak acid. And when we have ammonium as a conjugate, it is going to give a weakly acidic solution. So 5 would make sense because ammonium is present, right? These other salts like the cesium, the potassium, the rubidium, the sodium, these are all just basic earth salts that we're looking at. They would not constitute any type of acidity, at least in the sense of hydrogens with pH. And remember, pH is directly looking at the acidity factor based on H plus or H3O plus in solution. That's how we measure pH. So the other one that sort of has it tucked away or hidden is when you talk about bisulfate. Okay, so whenever you have something, a lot of people know about sodium bicarbonate because that is an example such as where you have a hydrogen attached to the carbonate ion. But sodium bisulfate is going to have a hydrogen available. It would be NaHSO4. All right. So what we're really looking at in a case like that is you have H2SO4. That would be a very obvious acid, sulfuric acid. And then you can go and take one of those two off because it's diprotic. So you can replace with the sodium and you have NaHSO4. That's going to be sodium bisulfate. And then again, you can lose your second acidic proton and you would have Na2SO4. Now, this, the H2SO4, would certainly be the most acidic. Okay? So this would be very acidic. Then you get to the bisulfate. This would be weakly acidic because we are talking about having already removed one of the acidic protons. And in this case, your second proton is going to be far less acidic than the first proton was. Remember back when we talked about diprotic and triprotic, polyprotic acids, that each subsequent proton that gets removed becomes more difficult from a Ka standpoint to get off of that molecule. However, weakly acidic is still acidic, so that would be acidic enough. So 7 would also work here. Okay. Again, 8, you're talking about sodium cyanide. That would not be because you just have sodium and then the nitrile type of functional group there. So we're really looking at 5 and 7, and that would leave D as the correct answer. So the rest of these would all be out. Again, the key is look for hydrogens that would be available to participate in some sort of acidic environment. All right, now 3. When asked to titrate 30 milliliters of 10 molarity HNO3 with 0.1 molarity NaOH, a student chose thymol blue as acid-base titration indicator. The indicator changed color from yellow to red when 20 mils of the sodium hydroxide solution had been added. what was the pH of the solution at the titration endpoint? So what you need to do here is use a little bit of math. We were asked to titrate 30 mils of 0.1 molarity HNO3. So in order to figure out the moles of HNO3, we first want to realize that we have HNO3 and NaOH being added together. And what that's going to produce, because this is a strong acid and a strong base, we're not going to talk about equilibrium. We will get H2O, and we will also get sodium nitrate, NaNO3. So these will be the two products that we come up with in a one-way reaction. This is a 1-to-1 molar ratio when we look at the balanced equation. So that is to say, for every 1 nitric acid, I require 1 mole of sodium hydroxide to neutralize it. So what I want to do is find the moles of nitric acid that were originally present. And I can do that by taking the molarity, which is given in the question, and solve for X in the molarity equation. Now, it gives us 30 milliliters. We're going to convert that to liters. And when you do that, you just multiply 0.1 times 0.03, and you're going to find that X, and in this case we're dealing with HNO3, okay, is 0.003 moles of HNO3. All right, now, it also told us how much sodium hydroxide was used in order to obtain the endpoint. So same concentration. You notice the concentrations are the same. It allows for some easier math here. Okay, only 20 mils was used. So X, in this case, is going to be 0.002 moles of the NaOH that was consumed. Now, what we want to do is take the difference here, because we obviously have some leftover acid. 0.003 moles minus 0.002 moles. Okay, so this was the HNO3, and we can do this because it's a 1-to-1 ratio. And we're left with 0.001 moles of HNO3. And that is the amount of moles of acid left after we hit that 20 mils of sodium hydroxide in the solution. All right, now, what is the molarity of the HNO3 after the sodium hydroxide? Now, why is that important? Because when we're looking at this, right, we want to find pH. Well, pH is going to be the result of the hydrogen, and the hydrogen is directly a result of the HNO3, because the HNO3, every HNO3 can give off an H+, in this case. It's monoprotic. So if we can find the molarity of the HNO3, then we can find the molarity of the H+ that is left in solution, because it would completely ionize as a strong acid. So hopefully everybody's still with me. What we're going to do is take 0.001 moles of the HNO3. That's what's left. Now here's what you have to keep in mind. The volume has now changed. It was 30. However, we have added 20 milliliters of aqueous sodium hydroxide. So we now have a new volume, which is going to be 50 milliliters, right? So if I solve for this, I then end up with 0.02, and this value right here is going to be the molarity of HNO3. So once I have this value, I can associate this directly as the concentration of H+. So all that I really need to do is take the negative log of that value, which we can put as 2.0 times 10 to the negative 2. And that's just a rewriting of the 0.02 there. And when I take the negative log of this, I'm going to end up finding 1.70. This right here is the pH at the equivalence point. So B would be the correct answer here using the math. Now, let's take a moment to discuss this indicator. The indicator that was used was thymol blue. Now, thymol blue is used when you have an acid solution, an acidic solution. So because we're using a strong acid and a strong base, the real proper point of neutralization, okay, when everything has been used up, is going to be near a pH of 7, because we're talking about a strong acid and a strong base. Remember back to the titration curves. So this was a poor choice of indicator to pick out. And the reason for that is that the color change, which signifies your end point, was occurring long before all of the hydrogen had been used up in solution. So this was not a good indicator. A better indicator would have been something that could have dealt with a pH range at 7 or slightly above 7. So maybe something like phenolphthalein is a very common indicator for something around there. However, when you do thymol blue, you're talking about somewhere in the mid 1 to the mid 2 range for pH. So maybe like a 1.5 to a 2.6, 2.8, somewhere in there. So that is not a good idea unless you're looking to monitor pH in that region. Okay, maybe you're looking for a buffer that's in that region when it generally slips out and starts climbing above a 2.6, for instance. However, to have this indicator choice for a strong acid, strong base would be a very poor choice of indicator. All right, now that wasn't really the point of the question. However, it's important to realize that just because the indicator has changed color does not mean that all of the acid and base have reacted as far as the complete 1-to-1 ratio. We still had acid left. You have to be very careful about which indicator you pick for what type of titration. So hopefully that makes sense to everybody. All right, so that pretty well wraps up what we wanted to look at here. So this will conclude our lectures on acid-base chemistry. And as always, thank you for learning with MCAT ACE, and we will see you for additional lessons soon. Take care, everybody.